Welcome to Mastering Distributed Transactions. In today's connected world, building reliable and scalable distributed systems is more important than ever. But as we piece together services and systems across different domains, managing data consistency becomes a formidable challenge. This tutorial will guide you through the intricacies of distributed transactions and introduce you to the SAGA Design Pattern, a strategy that ensures consistency without locking your system into long-running, locked transactions. By the end of this session, you'll have a clear understanding of how to implement the SAGA pattern to design robust distributed systems that can effectively handle complex multi-step transactions. So, let's embark on this journey to enhance your architectural toolkit and simplify the complexities of distributed transactions. Stay tuned as we unravel the concepts, walk through real-world scenarios, and dive into practical implementations that will bring the SAGA design pattern to life. We will understand choreography versus orchestration, real-world scenarios, and the implementation of SAGA.
Challenges: need for managing transactions in distributed systems. As we delve into the complexities of distributed systems, it becomes evident that managing transactions across multiple services poses unique challenges. Unlike in a traditional single database environment where ACID properties, atomicity, consistency, isolation, and durability guide us, distributed systems introduce a layer of complexity that demands a nuanced approach to ensure data consistency and system reliability. First, let's consider network issues. In a distributed landscape, services may span across various servers or even geographies. This introduces latency, risks of partial failures, and network partitions, all of which can disrupt the seamless coordination necessary for transactions across different services. Next, we encounter the challenge of data consistency. How do we ensure that all our services, each potentially owning its piece of the data puzzle, remain in sync, especially in the face of failures? This is no small feat, as the autonomous nature of microservices, designed for independence, clashes with the inherent need for coordination in transaction management. This leads us to another critical point: service independence. The essence of microservices is to operate autonomously, yet transactions require a level of coordination that seems at odds with this principle. How do we reconcile these conflicting requirements without compromising the core benefits of microservices? Lastly, scalability comes into play. As we aim to expand and grow our systems, the task of coordinating transactions across an increasing number of services can become a bottleneck, impacting performance and scalability due to the heightened overhead and complexity. In the absence of an effective strategy to manage these distributed transactions, the risks are significant. We could face data inconsistencies, leading to erroneous business decisions or system behaviors, degrade user experiences, or even encounter system-wide failures. This is why mastering transaction management in distributed systems is not just a technical necessity but a business imperative. It's about ensuring the integrity of our systems, maintaining consistent and reliable user experiences, and safeguarding the continuity of our business operations. As we move forward, we'll explore how the SAGA design pattern emerges as a strategic solution to navigate these challenges, offering a structured approach to managing distributed transactions with precision and efficiency. In the realm of microservices architectures, where transactions are distributed across multiple, often disparate services, maintaining consistency and managing data flow can be a Herculean task. This is where the SAGA design pattern comes into play, a sophisticated strategy that ensures data consistency without depending on a centralized database's ACID properties. The core purpose of this pattern revolves around three pivotal principles. Firstly, data consistency. The SAGA design pattern is specifically designed to maintain a consistent state across various services within a distributed system, even when faced with partial failures. It acts as a guardian of data integrity, ensuring that each service can independently arrive at a consistent end state. Secondly, decentralization. By enabling decentralized data management, the SAGA design pattern perfectly aligns with the microservices principle of distributed data ownership. This allows for greater flexibility and scalability, as each service manages its own data and transactions. Thirdly, resilience. In the unpredictable world of distributed systems, the ability to systematically handle failures and rollbacks is not just a feature, it's a necessity. The SAGA design pattern enhances the resilience of systems by providing a structured method for responding to and recovering from failures. Diving into the core concept, a SAGA is not a standalone entity but rather a sequence of local transactions. Each of these transactions is responsible for updating the database and sending out an event or message that triggers the next local transaction in line. It's a relay race of operations, where each service passes the baton to the next. However, if one runner falters, if a transaction fails, the SAGA is equipped to execute compensating transactions. These are the mechanisms that revert the changes made by previous transactions, effectively undoing actions to maintain the system's consistency. But why do we call it a SAGA? This term is a metaphorical nod to the epic tales of old, a long, involved story, marked by a series of interwoven events. In our context, it represents the series of transactions that, when linked together, complete a larger and more complex business process. The SAGA design pattern, therefore, is not just about individual transactions, it's about the grand narrative of operations that, together, achieve a common goal in the world of distributed systems. In our exploration of the SAGA design pattern, it's vital to understand the main components that bring this strategy to life. Each of these elements plays a specific role in ensuring the seamless operation of distributed transactions across different service domains. Let's start with local transactions. These are the individual steps of a SAGA, where each one operates within the boundaries of its own service domain. The role of a local transaction is twofold: first, to make necessary changes to the service's own data, and second, to act as a catalyst for the subsequent transaction in the SAGA by signaling its completion. Moving on to compensating transactions. Think of these as the countermeasures to any local transaction. Their role comes into play when a subsequent step in the SAGA fails. These transactions are uniquely designed to semantically undo the effects of a previous local transaction, thus ensuring that any partial changes do not leave the system in an inconsistent state. Next, we have events or messages. These are the communication lifelines of the SAGA. Once a local transaction is completed, an event or message is generated to indicate this completion. Their critical role is to act as connectors, signaling the next service in line to execute its transaction, ensuring a coordinated flow through the SAGA. We also have event/command handlers. These components are vigilant listeners, responding to the events or commands relayed between services. They are the executors, carrying out the business logic tied to each step, including triggering any compensating transactions if necessary. In the case of orchestration-based SAGAs, we introduce a transaction coordinator. This is essentially the conductor of the orchestra, managing the execution of the SAGA. It instructs each service on what transaction to execute next and seamlessly steps in to handle compensating transactions when things go awry. Lastly, there's the distributed SAGA log. This component is the chronicler of the entire process, maintaining a persistent record of all events and transaction states associated with the SAGA. Its role is crucial for tracking the SAGA's progress, ensuring that every transaction in the sequence is durable and reliable, and aiding in the recovery process if needed. Together, these components form the robust infrastructure of the SAGA design pattern, each with a distinct responsibility, working in harmony to navigate the complexities of distributed transactions. When we talk about SAGAs in the context of distributed transactions, it's crucial to understand that there are two distinct types we can implement: choreography-based and orchestration-based. Each has its methodology and ideal use cases. Let's begin with choreography-based SAGAs. In this type of SAGA, there's a dance of sorts where each local transaction knows the next step in the sequence. There's no master conductor; instead, each service independently produces and listens for events in the system. This decentralized approach allows for a more flexible and autonomous system architecture. Services communicate through events, and when they receive an event, they decide what action to take next, without being told explicitly by a central authority. This gives each service the flexibility to evolve independently, promoting a loosely coupled system. On the flip side, we have orchestration-based SAGAs. Think of this as having a central conductor, the SAGA orchestrator, which directs each participant service on what transaction to execute next. Here, the orchestrator holds the baton of centralized control, making all the critical decisions and issuing commands to the involved services. This centralized approach ensures that coordination and progress monitoring are tightly managed, and if a service transaction fails, the orchestrator is there to systematically handle the failure. When comparing the two, it's essential to weigh the pros and cons. With choreography, we gain enhanced autonomy for each service and reduced development complexity, which works well in naturally event-driven systems. However, the downside is that the business logic can become scattered, making it difficult to visualize the overall process. With orchestration, the benefits lie in centralized visibility and control, simplifying the management of complex business logic and handling compensating transactions in a streamlined manner. The con here is the potential for a single point of failure, which could bring down the entire process. Additionally, this method can create a dependency chain between the orchestrator and the services, which may be counterintuitive to the microservices philosophy of independence. Understanding these two approaches to implementing SAGAs is pivotal in choosing the right one for your system's needs, balancing control and autonomy against complexity and resilience. In the SAGA orchestration pattern for a food delivery app, a centralized orchestrator is key to managing the interactions between various services, ensuring a smooth and coordinated process from order placement to delivery. Here's how the orchestrated SAGA unfolds. 1. User places an order. A customer uses the app to select their items and place an order. The order service then captures this order, creating a new record in the database with an initial pending status. It then signals the orchestrator to kick off the SAGA. 2. Orchestrator steps in. Upon receiving the signal, the orchestrator springs into action, guiding the flow of the entire SAGA. Its first task is to ask the restaurant service to confirm the order's feasibility. 3. Restaurant service confirmation. The restaurant service, upon receiving instructions from the orchestrator, checks the order's details, like item availability and preparation time. It then reports back to the orchestrator, confirming whether it can fulfill the order. 4. Orchestrator's decision-making. With the restaurant's response in hand, the orchestrator decides the next course of action. If the restaurant confirms the order, it's time for the payment service to swing into action, tasked by the orchestrator to process the customer's payment. 5. Payment processing. The payment service, upon orchestration, tries to process the payment, informing the orchestrator whether the payment goes through successfully or not. 6. Post-payment orchestration. If the payment succeeds, the orchestrator then delegates the task of assigning a delivery partner to the delivery partner assignment service. If there's a hiccup, like a payment failure, the orchestrator coordinates compensatory measures, possibly instructing the restaurant to cancel the order. 7. Delivery partner assignment. Once called upon, the delivery partner assignment service selects and assigns a delivery partner for the order, notifying the orchestrator of the assignment. 8. Final orchestration steps. With the delivery partner assigned, the orchestrator now sets the final wheels in motion, notifying the delivery service to commence the order's delivery to the customer. 9. Delivery service execution. The delivery service ensures that the order is picked up from the restaurant and delivered to the customer's doorstep, updating the order's status along the way to reflect its progress. Handling failures. A crucial aspect of the orchestrator's role is managing failures at any SAGA step. Should any service report a failure, the orchestrator initiates compensating transactions to rectify or mitigate the issue, such as reversing an order or issuing a refund. This orchestrated approach ensures a seamless, well-coordinated interaction between services, with the orchestrator ensuring that each step is successfully completed before moving on to the next, providing a robust solution for managing distributed transactions and handling failures efficiently in a food delivery app context. Here is an overview of the SAGA choreography pattern in action within a food delivery system. When a user places an order, the order service initiates the transaction by creating the order and setting its status to pending, which then publishes an order-created event. This event is picked up by the restaurant service, which validates the order and, based on the outcome, emits either an order confirmed or order rejected event. Upon confirmation, the payment service processes the payment and publishes either a payment successful or payment failed event. A successful payment triggers the delivery partner assignment service to assign a delivery partner, denoted by the delivery partner assigned event. Finally, the delivery service takes over to coordinate the actual delivery of the order, updating the status to out for delivery and eventually to delivered. Throughout this process, each service acts autonomously, responding to events, and thus completing the SAGA, ensuring data consistency and reliability across the distributed system. This illustrates the elegant choreography of microservices working together to fulfill a user's request. As our journey through the SAGA design pattern concludes, let's highlight the core insights and practical steps forward. The SAGA design pattern is crucial for distributed transaction management in microservices, ensuring system coherence and resilience in adversity. It offers our systems robust protection against failures, service autonomy, and fault tolerance. Implementing SAGAs does bring challenges such as increased complexity and the need for eventual consistency, but these are valuable chances to enhance our architectural skills. Let's take these key points into your workflows. Let them motivate your problem solving and success in your projects. Keep learning, experimenting, and collaborating, as this drives our collective progress in mastering distributed systems.